Hello, this is Mrs. Taylor's assistant. Today she's going to teach you about FTC graphically.
Right. So the example I'm going to use is out of Finney, Demana, Waits, and Kennedy's Calculus AP Edition Graphical, Numerical, and Algebraic textbook. It is number 59 from page 308, and the directions read, in exercises 58 and 59, f is the differentiable function whose graph is shown in the given figure. The position at time t seconds of a particle moving along a coordinate axis is s equals the integral from 0 to t of f of x dx meters. Use the graph to answer the questions. Give reasons for your answers. So they're telling us that the position is defined as the integral of f of x, and this is a graph of f of x. So you can kind of think of this as the graph of your velocity. And so if I integrate velocity, I get position. And the position would be represented as the integral, which means graphically it's represented as the area. And so using this interpretation, we can answer these questions about the velocity, acceleration, position, using this graph. So to start with, A asks, what is the particle's velocity at time t equals 3? Well, velocity is f of x. So when t equals 3, admit it. Wait, I think I got that wrong. Let me start over. What is the particle's velocity at time t equals 3? So if I think of velocity as the derivative of position, that means it's the derivative of this integral. And remember, derivatives and integrals are inverses, so they cancel each other out. So really what this is asking me to do is evaluate f at 3. And that would just be the corresponding y value. So when x is 3, looking at the graph, f of 3 would be 0. So the velocity at time t equals 3 would be 0, which means the particle is not moving. B, is the acceleration of the particle at time t equals 3 positive or negative? So acceleration is the derivative of velocity, which means it's the slope of velocity. So really what they're asking is, what is the slope of this graph at t equals 3? And we don't need a numeric value because they're just asking, is it positive or negative? And so if I look at the curve, it's increasing left to right, so that would be a positive slope, which makes the acceleration positive. C, what is the particle's position at time t equals 3? And so if this integral represents position and t equals 3, that means I replace this t with 3. And so now I interpret this as the integral from 0 to 3 of f of x dx, which means the area between the curve and the x-axis from 0 to 3. So graphically, it's starting at 0 and moves to 3. And so we're going to find the area of this triangle, which is 1/2 base times height. So it would be 1/2 times the base, which would be 3, times the height, which would be -6. Or just 6, depending on how you want to view it. But either way, your area will be negative because it's under the x-axis. So 1/2 times 3 times 6. 6 times 3 is 18. Half of that would be 9. So the area under the curve here, or under the x-axis here, would be 9, technically -9. And so the position would be -9. So D, the next question, asks, when does the particle pass through the origin? And so that is a position question. It's asking, when is the position 0? And so if we are representing position as an area, what we're asking is, where is the area 0? And so graphically, we are looking for the point where your total negative area and your total positive area are equivalent, so that when you combine them, you get 0. And that happens at x equals 6 right here, because if you think about it, this triangle and this triangle, they have equivalent areas one is negative, one is positive. So if I total that up, my result would be 0, making the position 0. So when does it pass through the origin? At 6 seconds. So the next question asks, approximately when is the acceleration 0? And remember earlier we interpreted acceleration as the slope of this graph because this graph represents the velocity. And so when is the acceleration 0 is asking when the slope is 0. And the slope is 0 when your derivative changes from positive to negative or negative to positive, which would be here at this maximum. So we would say at approximately 7 seconds, the acceleration would be 0. And it's an approximation because it's a graph. So every graph gives you technically an approximation. Question F is asking about the direction the particle is moving. So it's asking when is the particle moving toward the origin, which would be to the left, and away from the origin, which would be to the right. And remember, velocity is directional. So when velocity is negative, it's moving left, the particle's moving left. And when velocity is positive, the particle's moving right. And so remember, this graph technically is a graph of the velocity. So when your y values are negative, that means velocity is negative, and the particle is moving to the left. So our particle is moving toward the origin from 0 to 3 seconds, because that is where all the negative y values are. And then it's moving away from the origin to the right from 3 to, I guess you could say it's approximately 10, because that is when your y values are positive, making your velocity positive, making the particle move to the right. The last question reads, on which side of the origin does the particle lie at time t equals 9? And so this is focusing on total distance traveled, accumulation of distance and position. Because if you think about it, if I determine the position at 3 seconds, I would find the area of this triangle, which we discovered to be 9. And so that means that the particle itself, and it was a negative, so that means the particle itself was sitting at -9 on a number line. And then from 3 to 6, the area is the same, but it's a +9. So that means the particle went to -9, and then after this time interval, it's now located at +9 on a number line. And then all of this area past that is still positive area. So that means that particle continued to be on the positive side of the origin. So on which side of the origin does the particle lie at t equals 9? On the positive side. So that is how the FTC applies graphically, where we're interpreting the integral as a function and how that translates to a graph. We will practice this more in class on Monday.